without the mic in this room, I should be audible. Anyway, so good afternoon, everyone. Welcome to my support demo. I hope everyone is sufficiently sober from yesterday's beer event, or if not, they're at least at this what is it called? The Barnwell Peak. Oh, it's not visible. Okay, so today I'm talking about with how to orchestrate it with Kubernetes. I chose the title. I wanted to pick some catchy title, so I picked Clusternaut. Well, maybe some orchestration system may name it that way because not means sailor and cluster. You are the sailor of the cluster. Anyway, so yeah, I'm from Help, and I work in distributed systems at Yelp as a software engineer in the UK. Okay, so let's start with the topic. So what does Galera mean? It means different things in different languages. I believe in South American language it means prison, but I'm not talking about prison here. So this is about a boat, where people are rowing synchronously. When you are rowing a boat, I believe you should do it in a perfect synchronicity, otherwise, you may tumble or something. The same thing is, the same principle is reflected in the cluster as well, in a synchronous cluster. Kubernetes, what does it mean? It means helpsman. So it can be like this or that, if you are into like Star Trek and stuff, you may know what, he was also the helpsman. Anyway. So Kubernetes means the helpsman. In turn, so you're sailing the boat. And when a boat is like this, you need a pretty powerful helpsman or orchestrator, for a cluster like this. So I just made this Star Trek Enterprise. Anyway. Okay, so I believe there was a talk today morning about pets versus cat in a distributed system. For those who are not aware of it, it depends on how you treat your node in a cluster or a box. Whether you treat it like a pet and then you give it a name and you treat it with fondness, or you treat it like cat. When any of them are sick, you replace them. Anyway, here what I mean by DCOS is data center operating system. It's a term which was popularized in a paper from Google, I believe, in which what they mention is that you treat every node in a cluster not as an individual node, but as a set of resources, and you can allocate your services on them dynamically, and so that you get better utilization and reliability. Anyway, so some of these are the DCOs present. So today the one with Kubernetes I'm going to talk about is with reference to GCE or Tectonic, both of which support Kubernetes. Mesos also does it, but I think it's at alpha. Microsoft Azure also supports it, but I haven't tried that. Anyway, so what's the rationale here? As I said, we are looking whether you are looking from the perspective of a node or a host. What I mean by that is, when you are thinking of a node, you're talking about a physical box. But more and more, we are moving towards an architecture where we are less concerned about the boxes and more about, a place where we can deploy our services irrespective of where they run. So it needs to be agnostic of the location or the hardware where it's going to run. And most of these DCOs that I mentioned earlier use a lot of reusable components, like the pastor that I mentioned earlier, that I had written earlier, uses a lot of reusable components such as the DNS, or for service discovery, something like Smart Stack, for monitoring, Sensu, or a lot of other things, for logging, And as you can see, some of these have been turned into plugins into latest container systems such as Docker. And that actually helps when you're deploying something such as these with the orchestrators such as Kubernetes. And as I said, the agnosticity is also very important. And when I say agnosticity, I don't just mean the location agnosticity, but also in terms of the API. When you're talking about these components, you should be able to glue them effortlessly, and you should be able to do it. They should be like very loosely defined APIs so that you can replace them or you can add more of them or compose them. Anyway, so for the kind of architecture I'm talking about for the Kubernetes, the one at least that is defined on the Kubernetes side for as like reference architectures are some of them, including like client server based, that you have like a bunch of clients and then a server, multiple nodes in a server, of course, or a multi-layered one, which is more common in organizations where you have client, then several first level of the servers on the edge, then the mid-level web servers, then the database servers. So that's the kind of architecture that is intended for use by Kubernetes. Next thing is scaling. So as you may know, there are two kinds of scaling. You scale either horizontally or you scale vertically. But which one is more preferred? Well, I may be kind of biased towards this, but I believe that the approach is more towards horizontal scalability than a vertical scalability, because scaling vertically implies that you do not scale the service, but you scale the one of the nodes of the service, and I don't believe it can be done as elastically as possible, as or intended. The next thing is the statelessness in database, and this is very important, because when you're using service, past service, you generally require the planes, the control and the data plane to be separate. And what I mean by this is you should be able to change them. You should be able to change them without impacting the other planes. And I see this is being implemented in something such as MySQL cluster. If you used MySQL cluster, you can see that they have like the storage plane is separated from the control plane. That's a good example of that. And I believe Google Vitess also has something like that. Okay, next thing is I'm talking about elastic scalability. What I mean by that is, and this is when people generally talk of scalability, they talk of scaling, upwards, adding more nodes. But what they do not, what most of the scalability discussions do not talk about is scaling down. Scaling down and scaling up. Scaling down is something that has its own challenges in most of the, and it's kind of the weak point in many of the architectures. And I think that, so the scalability also needs to be elastic. And the reason I stress on this is because if it's not elastic, there will be a general impedance towards scaling upwards, because many times, because the traffic in on the web, it can be a spiky one. You may have like a spiky traffic just on the weekend, and during the weekdays you may not have it more. So having a kind of, and maybe this is not on all weekends, maybe only during holidays, stuff like that. So you should be able to scale up and down quite elastically. The next thing I just want to talk about is declarative versus imperative, and this is also very important, I believe. And this is something that has been there for a while in configuration management systems, Puppet, Ansible, Terraform, and whatnot. And I think this is important because it helps you to compose your microservices better. And this is very important because as developers, we develop, like such as, for instance, if you develop like a Python service, initially you run it inside your virtual ENV, and then you try to scale it upwards. That is, first you run as in an application level isolation, and then you try to run it in a operating system level isolation, and that way. So you try to move it, and that's very important when you are using. And that's very important when you're using the declarative paradigm rather than imperative one, because with the declarative one, and this is something I found in somewhere in in some other slide, and it says that you need immutability is very important there. That is, what runs on my laptop, it should be equally reproducible and not identically, but equally reproducible on server, and that's very important, I believe. And I think some of the principles are also summarized in the 12-factor app, which I believe was put forward by the engineers from Heroku or someone, and that they also stress the composability factor a lot there. And with these Lego blocks, I was trying to illustrate the principle of composability. Okay, so this is just a slide about containers. I believe, it has been there in our tech space for so long, it may have become cliched now. Anyway, I'll just mention it anyways. So what's a container and why should I care? So this is, just to mention in 3 words, it's just operating system virtualization as opposed to your para-virtualization or full-scale virtualization in like Xen or KVM. So again, what's the core? What lies at the core of a container is mainly isolation. And as I said, there are several hierarchies of isolation, as I would like to say. When you have something like an application level isolation, you are running it inside a sandbox, an application level sandbox. Then you'd like to scale it to a container which uses C groups and namespaces. Namespaces being something such as PID network or mount namespaces, so that there is a sufficient level of isolation. And then you have like SecComp for filtering the syscalls. And the namespaces is what I wanted to concentrate on. The next thing is there are the latest unique kernels have been there for a while, and they have been in the news recently as well. Anyway, so unique kernels and VMs, what is their role? And I would like to mention that while people are talking excessively about containers, it's also important to consider the role of VMs, because the unit of processing, what I've seen, it doesn't have to be bare metal, is what I'm saying. It can be like a bare metal, VM, and container, because for several reasons, many deployments require isolation which may not be met by a container. You may require a much higher level of isolation, so the VM is the second level, and above the bare metal. Anyway, some of the contemporary container solutions are like LXC, which has been there for a while and which is very mature as well, I believe. Of course, Docker, then Rocket, Runc, which is the unified kind of thing, and then you have Jails in other operating systems, and Solaris has its own, and let me contain that for you from Google, which I'm not sure is open source yet, which actually they use instead of Kubernetes internally, it seems. And then you have like systemd and spawn, which, anyway. So this is like a really short intro to Galera cluster. I believe there is a talk from Fred late in the evening at 6 on demystification of Galera. So this is basically a MySQL. Every node in a Galera is MySQL, InnoDB specifically, and it implements what you call as a right-side replication API. And you have like a Galera plugin which implements the API, which actually implements the logic of group communication and synchronous replication. And I mentioned it as a virtually synchronous replication because only the parts which are necessary to implement ordering and reliability are the synchronous ones. But for optimization purposes, the parts that do not require you to have the reliability or the performance are not fully synchronous. Anyway, I would still defer to the talk from Fred on demystification of that. Anyway, and this is mostly a certification-based concurrency, and what that means is when you have like a conflict, you use optimistic concurrency control rather than pessimistic concurrency. The latter being where you use like logs, which do not scale over a distributed system anyway. So this is how the layer looks, and like the DBMS is InnoDB here, and you have all these things. Yeah, as I said, it's a synchronous replication. And I believe there was a talk earlier today from Diego on group communication, MySQL MySQL group replication, which are also which may not have the same architecture, but which implements the same principles. And I believe at least it used corrosive earlier. Anyway, so what's next? So what I'm going to mention here is how does this fit? Normally when people talk about implementing databases on such systems, they mention that it needs to be stateless, so that you can easily move around, because data is a huge factor, and moving data around is not that simple. So either they talk about stateless databases, or the ones which have like separate planes of control and data, so that you can control planes easily and keep the data wherever it is. As I said here, MySQL is one of them. And how does Banana fit here is because it's, as I said, it's a synchronous replication. And with that, since it also has like an automatic node provisioning, all the nodes are symmetric. The symmetricity is what helps here, and that's what ensures the idempotency when you are provisioning the cluster. So that is, you can use like a template and you can provision all the nodes of the cluster, which helps with something such as replication controllers of Kubernetes. If you're not familiar with it, I'll just come back to it. And for someone who is wondering whether what kind of what subset of cap implements is basically a CPC. That is, if you have like a partition, there will be one partition which is a primary component which will be available always, but the other partition will only support something like a dirty read. Okay. Now coming to the main gist of the talk. Okay, what is orchestration? And there are some really definitions of service-oriented architecture definitions of orchestrations, which talk of stitching or composing diverse services. And there is something like choreography. Actually, when I was doing some research on these terms, I came across the concept of choreography of services, which seemed a bit facetious, but again, what it implies that the concept that I mentioned earlier, where you use like many reusable components such as logging or DNS, and you try to have them and you try to use them as like one service, that is the sum being greater than the total, something like that. And you define the protocol in which they can. You either define the protocol or you make the services aware, or actually on the other side, agnostic of the protocol. Okay, so coming to Kubernetes itself. So these are the main constituents, but not the ones that are applicable here. You basically have something called Kubernetes, which runs on every node, and which implements the Kubernetes on every worker node. This is not the master node. There is a master node which implements stuff like scheduling and all that, but I'm talking about the worker node. And you have like something like pod, in which you like, a pod is basically a collection of containers, logical collection of containers which share the same network namespace. And I believe they can also share volumes, because that's how the pods are scheduled. That they are scheduled on the same physical node or physical VM. Sorry, on a VM or physical node. So in a pod, you can have like a main service such as like a MySQL running and any of the associated auxiliary helpers for it. And there's a concept of services in Kubernetes, which is basically an endpoint with which clients can access the servers, or in case of Galera itself, the servers can talk to each other independent of the physical addresses of the other nodes. And this is very important because in a dynamic situation where servers come and go, the knowledge of their physical addresses, physical IP addresses, is less important, and having an endpoint which ensures that the quorum of the cluster is maintained is more important. And then you have something called replication controller, which basically what it ensures is, if you are familiar with the concept of auto scaling in AWS or something like that, this is something similar to it. That is, it ensures that you have like a single. You can say that you want 3 nodes in a cluster, and if one of the node crashes due to a bug or something else, this ensures that another node is provisioned. When I say node, I don't mean the physical node, but a node in the cluster, a node in the Galera cluster, a virtual node, just to put it that way. So it ensures that the minimal, the minimal number of replicas remain. Then you have the concept of labels and selectors. Basically, what you can do is you can attach metadata to every node in terms of name and the service and all that, and you can use selectors to uniquely identify any subset of nodes. And this is kind of familiar to us from Puppet, like Puppet types, using M collective to uniquely identify a subset of nodes. Something similar to that. Yeah, so this is the basic architecture or how it is. So in case of Galera, this is how each container will look. Each Galera node will be running inside each of these pods, and C advisor is basically used to collect metrics and stuff like that. And it's not unique to Kubernetes. But it has been used mostly with Kubernetes, I believe. And this proxy is what is used to implement a service endpoint. And this is the actual master node. And I'll come to each of these things soon. So this is how it looks basically. So I just wanted to mention others which are used similar to Kubernetes, something such as Fleet or with Mesos, you have those things. Anyway, so what is a pod? Pod is basically a collection of, as I said, a collection of related containers. So it's like a pod in an office, where you are the main guy, and there are other things in your pod which help you with stuff, or your laptop, for instance. Anyway, so what do they contain? The containers are. And how is the grouping done? The grouping is, as I said, it's not a physical grouping. You cannot physically group the containers in any way like that. It's more of a logical grouping, so that they are co-located on the same node, so that they share the same network namespace. And when I say network namespace, what I mean by that is, suppose associated service want to refer the main service, it can directly refer to localhost and the port combination rather than an IP address and a port combination. Which is very helpful when you're running something such as a health check as a separate service, for instance, or a HA proxy, for instance, if you're running along with the Galera node itself, then that is very useful as well. That's very useful. And port communication is something I'll refer later. And yes, you can attach a label to ports so that you can refer to them. And this is very useful when you're trying to use a client to either bring them up or down. For various things. So this is how a service looks. So you have in case of Galera or Galera cluster or Xtradb cluster, all these pods contain each of the MySQL is running inside them, and they expose in that case the 3 ports, and a client can access. And what additional benefit is provided by this service endpoint is it also provides you a load balancing, which can also be very useful. Anyway, so this, I just wanted to mention that you shouldn't commingle it with the microservices, because the term services has been it's not been used as a synonym for microservice, but it's more of an endpoint here. So think more of an endpoint with which you can refer to other nodes or clients or another layer of your architecture. Okay, anyway, so how is the communication? What is the purpose of a service? That's more important. And I believe it's for the communication, at least in this case, I'm using it for the communication between the nodes, because when nodes dynamically emerge or die, you do not want the cluster to go down, but the endpoint to still remain up based on the other nodes in the cluster, and service abstraction is what helps in that. So that when you refer to this, and I'll tell you what I'll show you how the abstraction is done. And this communication of the service happens to each node through either environment variables, like how you have it with Docker, environment variables which are exported and available inside the container, But having this environment variables imposes an ordering requirement, which means that you need the service to be up before the load is up. Otherwise, that can be a problem. But it's much easier with the discovery. With the DNS, the problem is there are several issues with DNS, and something that has been solved with better discovery mechanisms such as Smart Stack. But Smart Stack is not available in Kubernetes, so it's either of these two things. So the problem with DNS is the problem with TTS, or the problem with clients which do not, or the libraries which implement DNS in different ways, which can introduce significant issues with your architecture, with your SOA architecture. And so replication container, as I mentioned earlier, it uses basically a template, and it ensures that a minimal number of nodes are up. It's more of an init for a cluster, but it can also be used for like rolling updates or multiple versions. Suppose you want to run like multiple versions of if you want to run Galera cluster with a subset of nodes on a higher version, but with communication compatibility, you can do that. You can say that, and you can assign node. Replication controller doesn't have to be one. You can run multiple replication controllers, with each managing a subset of nodes. So it's more of like a herd management in terms of the analogy I mentioned earlier of pets and cattle. And this is next thing is networking. Network is very important in Kubernetes, at least to not for the users, but for the people who try to have Kubernetes of their own, rather than on GCE or Tectonic or anything like that. So the way it works is instead of so there are three kinds of communication, actually three, but I just want to do one more. Communication which requires pod to pod and pod to service, and intra-pod and external to service. When I say external to service, it means from a client, from an external client which is outside your architecture. An intra-pod being, as I said, from like a HA proxy which is running alongside inside the pod itself. So you can refer to it as localhost. Pod to pod being between the nodes of the cluster, and pod to service. In this case, the pod to service and pod to pod are kind of overlapping, because the service endpoint in turn is not another client but the server itself, because this is a symmetric cluster, right? And to ensure this kind of networking, you can use these things with Kubernetes, but the one on GCE uses Google Compute Engine, the one on Tectonic I believe uses Flannel, but there are others such as Open vSwitch and Calico and Vue. As I said, this linking is not the Docker style of linking. When I say Docker style linking, it is the one that we had since the inception, where you link the container and it gets its etc host updated with the new container. That's not how the linking works, and that's kind of an anti-pattern here, because as I said, for a cluster, it's more dynamic, and you don't want such. You want the newer nodes to be known to the older ones, and vice versa. Anyway, so these are the external components which are there. As I said, the earlier components are the ones that run with the services. So these are the external components. Of course, you have like a container registry, which in some cases is QA, or in case of Google, there's a Google container registry. You have the scheduler, which I believe also is pluggable now. I believe there was a talk just a few, I believe 1 hour back from Kubernetes on how to write custom schedulers and use metrics to auto scale your cluster. Of course, it provides a REST server and C-advisor, and FluentD. FluentD is used for logging in some other places, but on Google Compute Engine, it uses Google logging, so some kind of Google logging. Yeah, then you have XCD for ensuring for control management, something like Zookeeper. Anyway, so this is another example I just wanted to mention of. I would say that this is something that we have in-house at Yelp, and which was also recently open source. And this is more of less of an orchestrator and more of a choreographer. Is how I would put it, because it's a collection of loosely coupled components which are choreographed by some very simple and elegant utilities and client glue, I would say. So basically, it contains Docker. Actually, one more thing I would like to mention is Kubernetes not only supports Docker, but it also supports Rocket from CoreOS. Anyway, so this contains Docker and it uses Mesos, primarily Apache Mesos. It uses Chronos and Marathon for running the jobs and Chronos for scheduling the jobs. It uses Sensu for monitoring, and it uses SmartStack against DNS. There is a very good blog post on SmartStack, why use SmartStack instead of DNS. SmartStack also uses Zookeeper. SmartStack basically contains two components called Nerve and Synapse, where one of the component is basically a HA proxy running on each node, and which provides discovery information based on whether the health checks are running or not. Then we have Jenkins, and we have Splunk and SignalFx as well. Splunk is for logging, and SignalFx is for metrics. Next thing, I just want again this for how the deployment works. I just want to go quickly over this how the deployment of the Galera itself works with Kubernetes. So you declare and build your nodes. Yeah, okay. So you declare and build your nodes. Basically, it's a Docker file. The aim is to keep your Docker file minimal and simple. It should be, as I said, to keep it should not make any assumptions about the network or host name or anything, because having such assumptions binds those nodes and cannot be used in an environment such as this. If you declare a host name, let's say you declare a host name inside the container, you cannot use it, for instance, as an application controller, because you cannot use it like a template and spawn multiple nodes from the same thing. That's very important. I just want to mention that before Kubernetes, not before Kubernetes, but to run locally, I was using Docker Compose. And the issues had with Docker Compose was the same issues that I mentioned earlier when I was talking about services. It's that, and this is without the new Docker style bridge networking, lib network, without the lib network part. This is the old kind Docker networking, wherein the discovery of the nodes, mutual nodes, happens through updating of etc hosts and the unidirectional linking from the older and newer containers. Anyway, so how the mapping is done, it's simple. Each Galera node runs in a pod, and optionally you can run like HA proxy or Xtradb or other things alongside it in the same pod. HA proxy you can run if you want to run it inside a SmartStack, for instance. That way it provides the discovery. One more thing I would like to mention here is that Kubernetes also provides configuration to define health check, so that if a node is down, in general how it works is when your service dies, the pod is tried, the service is respawned by the kubelet itself, which runs on every node, and if the whole pod dies, or if the whole node dies, then the replication controller ensures that the pods are spawned on some other hardware node. For instance, if there is a hardware failure. So that's how the respawning works on different levels here. Yeah, so the health check API is also provided, so you can define your own kind of health checks. And I believe it was recently added to Kubernetes. It wasn't there a while back, and that's also very useful. So that you can say that it's not just when the service dies, but you can also say different ways of how it should be respawned. Anyway, so this, how the deployment works from, this is I'm using a Google Compute Engine again as a template for how I create Kubernetes. Well, you can set up your own Kubernetes, but that is outside the scope of this talk, and there are only 5 minutes left. Okay, so you create like a flat network. This is very important for Kubernetes, so that every pod gets its own unique IP address. This is very important to ensure pod-to-pod communication as well. That is, every pod, irrespective of its physical locality, should be able to connect to any other pod, either through a direct IP address or through a service. Then you create a cluster. This cluster is quoted because it's not the cluster, Galera cluster, but a cluster from Google Computing Engine perspective. That is the term that they use. And then you create like a service endpoint. These are the endpoints you create for internal cluster-to-cluster, node-to-node communication in the cluster. For externals, you use like 3306. So this is how the mapping is done, what I mean. You can map 3307 or anything like internally to 3306. And you expose and you have like session affinities. Okay, then you bootstrap a node. Bootstrapping a node, basically, and I believe this is a thorn in the shoe for most of contemporary distributed systems, where you have to bootstrap a node uniquely, and they cannot bootstrap each other. And then you start rest of the nodes from template, and you point to a service, Kubernetes service with a selector. That's what I'll show that faster, I believe, since we don't have much time. So this is how a service definition works, if you can see it. And this is how the Docker file is. This is, as I said, I've kept it really simple. And this is how the service looks. So you can define your session affinity and all that. Yeah. This is how you define an external service. And as I said, I put it as a load balancer, so you can get load balancing advantage as well. You don't need to use a separate load balancer if you're exposing your cluster to an external client. And this is how the pod definition looks. As you can see, I've defined. Well, one thing that may stand up here is that I've not defined how the code should be mapped externally. That's not required because with Kubernetes, as I said, every node gets a unique IP address. So you don't need to map how the code is exposed externally. That is taken care by. That's not required at all. Anyway, so this is how the command looks and all that. And this is how you can. This is the definition for an application controller. And so you can easily scale it. You can give it like a number of replicas, and it will create additional nodes. And if some of them die, it will spawn them again. This is how you use the labels here. So you can get the number of containers running, for instance, or for stopping them. The concept of labels and selectors is very, very powerful, and and it has been used not just in Kubernetes. I believe it's also used in CoreOS systemd services to attach labels to them. Anyway, so that's it. This is the credits. This is a further reading. Well, this is not exhaustive at all, but anyway, this is my contact. That's it, I guess. For more, of course, as yeah, you can ask questions, or as he's going to tell you in some time, there's going to be a dinner, and I'll be there, but not necessarily sober. But distributed systems are best discussed when you are imbibed, right?
Your answers are better when you are not sober. So it's good.
I guess. I don't know.
It's you think the answer is better, Fred.
Yeah.
So no question for you?
I thought 5 minutes was over. Anyway, thank you.
I was wondering, how do you manage the copy of data when you are spawning a new node?
Right. And that's a good question, and that's very important as well. I believe that and this I would answer generically. Well, in case of direct cluster, we have the node provisioning, which works automatically, because when a node joins, it contacts any of the nodes in the cluster. There is no concept of leader or follower, as you have in Xtradb, for instance. All the nodes are symmetric, all the nodes are same. So it contacts one of the nodes, and one of the node is chosen as the donor based on their state. And there is like a database state machine. Only the nodes which are synced can be selected as a donor, and then it transfers the data. There is a protocol for it. It's called snapshot state transfer. It's kind of like a tongue twister, snapshot state transfer. Anyway, so we have that, and that's how it works. And in case of something like Cassandra, it also, I believe that's a requirement to use your service. I wouldn't say requirement, but it's better to have something similar to that. Cassandra also has it. For instance, when you add a new Cassandra node, you can transfer the data and all that. And that's required. I would say it's desirable, not a requirement, but it's quite desirable to have something like that. Did I answer your question?
Yeah, but I was thinking about the DB of 1 terabyte, which can span
I know. Yeah. Well, as I said, you can also have a separation of control and data plane, which is also possible with MySQL, but it's not, there by default. You can of course separate your data plane from your control plane.